Everyone, in the previous video, we calculated the hydrostatic pressure at a depth of 2,500 meters under the ocean surface. Here, we're being asked to calculate the change in density of O2 in a balloon. The balloon is initially placed at a pressure of 1 bar and then taken to a depth of 2,500 meters. And at this greater pressure, it will experience a volume change and thus a density change. So to answer questions like this, I think it's really helpful to write out your state variables. So in this case, let's focus on the balloon at 1 bar pressure. Let's say at P1, well, the pressure is 1 bar. V1 is 10 liters, and T1 is 293K. Okay. Now it's asking us, what would it be its volume at a depth of 2,500 meters under the ocean surface at 277K? So our P2 will be what we calculated last video. We calculated the hydrostatic pressure using the formula hydrostatic pressure equals rho times G times H. And we got about 250 bar. About 250 bar. They give us T2, which is 277K. And we need to find V2. So that's our unknown. All right. So in order to find V2, we use our ideal gas law. Ideal gas law is PV is nRT. But R here is a constant. So because R is a constant, we can say that PV over NT equals R. And this relationship holds for any ideal gas. So because this is the case, that means the pressure state 1, or the volume at state 1, over NT1 equals P2 over NT2. Now the number of moles is going to stay constant since the same amount of oxygen is filling both of these balloons. We can cancel this out. And now all we have to do is plug in our variables and calculate V2. So P1 is 1 bar. V1 is 10 liters. T1 is 293K. And this equals P2, which is 250 bar, times V2 over 277K. So I'm going to move this here. And I'm just going to cross multiply here. So this will be 277K times 10 bar times liter equals 293K times 250 bar times V2. So these K's cancel out. We can divide by 277 to get 10 bar times liter equals 293 over 277 is about 1. We can divide by 1.06. So that's 10. Answer, which is 9.45. 4 times liter equals 250 bar times V2. And bars cancel out here. Divide by 250, we get V2 equals 0.037 liters. So now we have our volume 2. Now we're asked to calculate the density change. And that was the first step to calculating our density change. So let me just select this here, move it over a bit so I have more space. Okay, so it looks a bit messy, but we calculated our V2 to be 0.037 liters. And our V1 was 10 liters. So we've determined that our V2 is 0.037 liters and our V1 is 10 liters. And we need to find the percent change increase in density of oxygen. So density, rho, is given by mass over volume. So to find the percentage increase in the density of O2, we'd use the percent change formula. So the final density minus the initial density over the initial density times 100. And density, like I said, is mass over volume final, in this case, volume 2, minus mass over volume initial, which is volume 1. I wrote that. Go. Over mass times volume 1. Now, this is convenient. I forgot this times volume 2. This is convenient because we can multiply this out. So if we multiply this out, we get m over v2 minus over v1 all times v1 over m. And if we do this, we can cancel out these m's. And we get v1 over v2 minus 1. We distribute this. And our v1 is 10 liters. v2 was 0.037 liters. Write that prettier. So we do is divide, and we get 264. But don't forget to multiply by 100 when calculating percent change. We get big percent change. 264%